All right, so we're going to keep going now. As you probably figured out the other video, it loses the audio. So I actually finished the video not knowing that it wasn't recording me. So I have the notes written. I'm going to talk you through them here now. And I failed to mention too, all this stuff, these step 1, 2, 3, 4, all the way through, it's on your formula sheet. Okay, so all the steps, you don't have to memorize all these, you just have to be able to do them. Okay, so this is not, you don't have to memorize that step 4 is finding the extrema or anything like that. But, so our next one here, if you were to graph this guy, it's a quadratic, it's a shifted down 5 units. Okay, so for domain and range, it goes left forever, right forever. So it's all real numbers. Now the range, it would be -5. You think up and down, starts at -5. -5 is included, goes on up to infinity. So if you think about what's the smallest number I could get to come out for a y. Well, if I plug 0 in for x, 0 squared is 0, -5 is -5. There's no other way to get a number smaller than that. Okay, so on this one, that's kind of a way of, I guess, analytically thinking about it. Intervals of increasing or decreasing. If you look at this guy, kind of got those numbers filled in for you there. Think increasing, if I'm going from left to right, so if I'm thinking left to right like this, that graph is going up, 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 up to there, and it stops. So I'm going to use x values to describe where I'm at. Okay, so going left to right, start at -infinity up to -3, it is increasing. The next time it's increasing is down here, so it picks back up at 1, up to 2. Again, I'm using x values to describe where it's increasing. And then skip over to 4 on to infinity. So the red marks I put in, that's where it's increasing. The places where I did not put a red mark is where it's decreasing. So starting at -3, this is actually going down as I go to the right. And then up here going down again. Okay, so think if you're a roller coaster riding this way, going from left to right, are you going up or going down? And typically you see I included these, it's kind of goes both ways with this. Or at -3, is it increasing or decreasing? Well, it's kind of doing both, because the step to the left of that was less than, that means it was an increase. The step right of that is less than, that means going to the right is a decrease. So it's increasing and it's decreasing at -3. Other people would argue that's not increasing or decreasing at -3. It's kind of a gray area in math. So, but we will include it though. We'll put it in there and include it. For the extrema, you probably heard of extrema. They're local and absolute. Now, another name for absolute is global. So absolute and global, I think global means like everywhere, like the whole world, or in this case, the whole graph. Whereas local just means within that area, or relative. So relatively close, kind of the way I think of it. So with this guy, let's see, if I look for absolutes on this graph, it has no absolute max because it goes up forever in this direction. So technically infinity would be its maximum. Infinity is not a number, so we don't include that. And then if I said what's the absolute minimum, well, it would also be -infinity because it's going down forever. Okay, so for global or absolutes, this doesn't have them. Locally just means within that area. Okay, so relatively speaking, if we're looking at this area right here, basically think of like if there's a hill or a valley, that's a relative min or a max. And when we're doing this, when we did increasing and decreasing, we used x values. Here we're talking about values, so we're going to use y values. Okay, this is location, this is actual value. So there's a relative max of 2 at x equals -3. So when x is -3, your value is 2. That's a relative maximum. Within that area, it's the highest point. But also at 1, or I'm sorry, there's a value of 1 at x equals 2. So here's another. So relative maxes, those are hills. Relative mins are valleys. Okay, so there's a relative minimum of -3 at x equals -1. And there's a relative minimum value of -1 when x is 4. So that's where that's coming from. Okay, boundness is just basically, is there something keeping it from going any higher? This first graph, it's not bounded above or below. It goes up forever and down forever, so there's no bound to it. This one here, it is bounded below because it goes down, it goes back up. So there's It's almost like there's something keeping it from going any lower than that. So this would be bounded below, but not above, because it goes up to infinity forever. So it's not bounded above. So basically, if it has an absolute minimum, it's bounded below. If it has an absolute maximum, it's bounded above. Here's an absolute maximum, it's bounded above. There's no absolute minimum, so not bounded below. Here there are absolute mins and absolute maxes, so it's bounded above and below. Now these numbers, I just made these up when I was first explaining it. I don't like the way I explained it the first time, so I'll skip over that. But I just made up a number of 3 and -1. I could have put 5 and -2, and it would have meant the same thing. Discontinuities. Okay, so these are basically if you're drawing the graph, if I can put my pen down, draw the entire thing without picking my pen up, then that means it's continuous. But if anywhere I have to pick my pen up, or pencil, whatever you're drawing with, then that's a discontinuity. And sometimes we think of them as a gap or a hole or a jump. There's just something where you had to skip. It wasn't smooth drawing. Okay, so both of these are holes, and they're considered removable discontinuities. So you remove something, you put a hole in the graph, that's a removable discontinuity. Now, sometimes they remove it and it's gone. Sometimes they remove it and they put that spot somewhere else. It's not really super important. They're both holes. They're both considered removable discontinuities. Okay, so like this graph, I'm going along, I have to stop, pick my pen up, draw that point, pick my pen back up, put it down here, and then keep going. Whereas here, I'm going along, I pick my pen up, put it back down, and keep going. So I had to pick it up. There's a discontinuity. So removable discontinuities, think of that as a hole. A jump discontinuity is where you pick your pen up, and then you put it back down somewhere else on that same x value. So it kind of jumps up. I didn't jump over and up. I just jumped straight up. Okay, that's a jump discontinuity. And on these, we're talking about limits. I don't know how well you guys know limit notation, limits from left and right. And basically, a limit is what y value are you approaching from the left and from the right. You don't have to actually get there, you just be approaching it. So like if this is a, this is an x value, that b is a y value, I say what value am I approaching as I approach a? So coming from the left, I'm approaching a y value. Coming from the right, I'm actually approaching the same y value. So if you're approaching the same thing, then that limit is there. The limit exists. It doesn't matter what the actual value is there, because like the actual value at a is up here. This is f of a. But as I'm coming from the left and right, I'm way down here at b. So these would both have a limit. The limit as x approaches a would be negative b. I just said negative b because it's b units down. So negative b. Yeah. And then over here on this guy, this limit, it's not approaching the same number because from the left side it's approaching 0. From the right side it's approaching some positive number. It's not approaching the same thing, so the limit does not exist. There's a limit from the left and a limit from the right, and that's how we put a minus means from the left and from the right. If these don't agree, then the limit doesn't exist. So I could put this up here, the limit as x approaches a on this problem of f of x equals does not exist, because it's not approaching the same thing on both sides. This is approaching the same thing on both sides, this is approaching the same thing on both sides, that one's not. There's a gap there, there's a jump. The infinite discontinuity. Okay, so that's whenever you couldn't, it's the gap between the two y values is so far apart, because coming from the left, I'm approaching negative infinity. Well, that is infinitely far away from positive infinity on this side. So basically when you have an asymptote, that's when you're looking at an infinite discontinuity. So yeah, I put from the left would be negative infinity, from the right is infinity, but the limit would not exist because they're not approaching the same thing. So you couldn't put a limit on that one. So now flip your papers over. Try to go a little bit faster here. End behavior. So we do limits approaching a point, because I had it as x approaches a on the last page. Now I'm going to do off to infinity and to negative infinity. So the end behavior is what's going on the ends of the graph. Okay. So the limit of this function as x approaches infinity. So it says what's your y value as your x value approaches infinity. Well, as my x value approaches infinity, my y value is also approaching infinity. That's why it's positive. the limit of the function as my x value approaches negative infinity, I'm flattening out here. The y value is basically 0. It never touches 0, but it's basically 0. So that's why the limit's 0. Here, going to the right, I'm going to infinity. Going to the left, I'm going to negative infinity. So that's where those come from. Let's see, the asymptotes. Just describing the asymptotes here. Hopefully this is review 2. You did this in algebra 2, but the horizontal asymptotes are these guys. So, I'm sorry, the vertical asymptotes are these guys. X equals -5, x equals 5. The horizontal asymptote would be y equals 2. And then for oblique is whenever you have one at an angle. And that's whenever the top polynomial has a power 1 higher than the bottom, you'll get an oblique asymptote. And we'll talk about that a ton when we get to that unit. But yeah, so an oblique, there is no oblique one on this one. Let's see here. Symmetry. I'm not sure if you remember this. I'm not sure if you went over this, but if it's symmetrical about the origin, which means if you rotate it 180 degrees and it's the exact same graph, then that's symmetrical about the origin. I guess I don't really have one here. Let me get my calculator out. I can graph one. Okay, so like here's one. There's a graph that's x cubed. That's y equals x cubed. Now let me rotate, like if you look how it's going, it's kind of an N shape going up and to the right. Now rotate 180 degrees. It's an N shape going up and to the right. So that would be an example of an odd graph. So it's odd is symmetrical about the origin. Odd, symmetrical about the origin. Notice the O's go together. Even means symmetrical about the y-axis. Think about opening the book. Symmetrical about the y-axis if you flipped it over. So for some examples here, this one would be symmetrical about the y-axis. So that's an even. This one's even, symmetrical about the y-axis. If you cut it in half, the left and right side look the same, and these two are neither. And again, this would be an odd. That's an example of an odd, because if you rotate 180 degrees, the exact same graph. Now, to check algebraically, what you're looking for here is, if I plug in negative x, what does it simplify to? So if I were to plug in negative x and simplify it, and I get the exact opposite of the original function, and that's odd. So opposite odd. Opposite odd, which is symmetrical about the origin. They're all O's. That's how I remember it. And then if it's even, when I plug in negative x and simplify, I get the exact same function I started with. Okay, so looking at this, here's g of x is x to the fourth minus 2x squared. I'm going to plug in a negative x for every x I saw before and simplify. If I take it to an even power, negative x times negative x times negative x times negative x is x, right? So it's the same thing as x to the fourth. And then negative x squared is the same thing as x squared, because a negative times a negative is a positive. So I get the exact same, when I'm done simplifying, I have the exact same function as I started with. So plugging a negative in for x didn't change it. Okay, so basically it means if I plug a positive number in, positive 6, and I plug in the opposite of that, negative 6, I get the same y value. So that's why it comes out even. Plug in negative x here. Negative x times negative x is x squared. But negative x times 2 is negative 2x. That's different than before. So I got same, different. That's neither. It's neither odd nor even. So just you put neither. And then here's an even one. Plug in negative x. Negative x times negative x is x squared. The 6, there's nothing to plug in for. So when I simplify, I come up with the original one. Again, like the one I showed you before. Let's see. FGH. Let's call it j of x, is x cubed. So if I j of negative x, that would equal negative x cubed. So that actually equals negative x cubed, which is the exact opposite of what I had before. So that would be an odd one, which I told you cubes, x cubed is odd. So that was the one I graphed. So here's graphically I can tell it's odd because when I flip it over, here's algebraically. Now the zeros, can you find the zeros of the graph? They go by different names. You can find the x-intercepts, you can find the roots, the solutions. Basically, it's what makes f of x equal 0. So you can use your calculator to look for zeros. You could factor and look for roots. Yeah, they go by all these names. So there's a quick video. I redid my video compared to what I did originally because I lost my audio. This is the second part of day 2.